Okay, so some follow-up comments on this confidence interval. So first of all, it is really important that these 150 planes were chosen randomly. So it says they randomly select 150 planes. So the sample must be chosen randomly. All of this is based off of probability, and if things aren't random, then our probability ideas don't really work the same way. you know, the problem would be if you check 150 planes and they're all like in the Northeast and it rains and snows there more, their wipers might be in different condition. So you can't choose all planes that are from one section of the country because they may need more wipers than planes from another section of the country, and you might overestimate. So you might think like, well, why don't we just like pick a selection of planes from the whole country? Well, even though it may seem obvious that places that get more snow need more new wipers faster than places that don't, there might be other reasons that planes need new wipers quicker that we aren't thinking of. So if we try to pick planes from all around the country, there might be some other thing going on that would be messing up the data that we aren't accounting for. And so we still end up biasing the data towards too many wipers or not enough wipers. So rather than be cocky and think that we know how to pick a broad choice of 150 planes that would be representative of everybody, the safe thing is just make it random. So if you make it random, there is some chance that you'll get a whole bunch of planes that need wipers or a whole bunch of planes that don't, but it's the nature of randomness that you sort of end up with a little bit of everything. And the bigger the sample, the more spread out your randomness is, and the more you're going to end up with a little bit of everything. So all of the math we're going to do is based off the fact that the sample is chosen randomly. And if you aren't choosing randomly, it messes up the math. There's ways to account for that, but that's much more complicated statistics than we're going to be covering. So second of all, the 150 planes that we have data for are called the sample. So I've used this word a few times. The sample is the stuff you have data for. The sample is supposed to be representative of some bigger group. And in this case, the bigger group is all the planes that that airline has. So the bigger group is all the airline's planes. That is the population. Okay, so whenever I talk about population, I mean sort of everybody, the group of everybody. And then the whole point of statistics is that it's not reasonable to check everybody in the entire population. So what you do is you check some subset of it, randomly selected. That's the sample. And then the results from the sample will allow you to guess what it is for the whole population. Now, sometimes you try to check everyone, like the US Census tries to check every single person. But normally that's not feasible. And the whole point of statistics is, doing like how you can compute estimates and how you can compute how trustworthy those estimates are when you don't have all the information, when all you have is a sample and you're trying to draw conclusions about the whole population. Okay, one last actual computation I want to do. Suppose that we want precision of plus or minus 5%. So remember, so can I just do plus or minus? Yeah, plus or minus 5%. So up here, our range went from like 19 to 34. So the population, the sample P was like 26%. And we were basically saying it could be like 7% lower or higher than that. So our precision here was plus or minus 7%. It was like a range of 7%, higher or lower. Let's say I want to get that down to 5% instead. So how do you get it down to 5% instead? Well, you need a bigger sample. Basically, the bigger your sample is, the tighter this range is going to be, the more accurate your estimate is going to be. Before I get to how to compute that, we need this number like this 2.57 we had before, or 2.576. So for a 99% interval, the endpoints are going to be 2.576 standard deviations away from the mean. That's the z-score of the endpoints. There's actually a number for a 95% interval. So for a, well, every interval has a number that goes with it, but 99 and 95 are the most common confidence interval like sizes. And so I have those memorized. So for 95% interval, the endpoints have z-score of 1.960. Okay, so I just have that memorized from teaching stats for a number of semesters. So we want the endpoints to be 1.960 standard deviations away, or standard deviations away from the mean, because we're doing 95% confidence intervals. And if we want a precision plus or minus 5%, then those endpoints should be 5% away from the mean. Okay, so let's just do our computation. So we know that 1.960, that is our z-score, so that it would be x minus the mean divided by the standard deviation. And I just said that, so x, that's the endpoint of the confidence interval. I just said if we're going to have precision plus or minus 5%, I want the endpoints to be 5% away from the mean. 5% in decimals, that's 0.05. That's the distance I want us to be away from the mean. And the standard deviation, well, that's a little bit messier. So I'm just going to put a sigma in there for now. And then let's isolate that sigma. So the standard deviation is where the n appears in the formula. The n is the size of the sample. How many are in the sample we have? So if we isolate our standard deviation here, let me just insert a page break. Well, if we isolate our standard deviation, that should be 0.05 divided by 1.960. And we have a formula for the standard deviation. It is the square root of p times 1 minus p. So p was 0.26. That's the proportion that need wipers in our sample. 1 minus p. And the number in our sample, that's what we don't know. Okay, so we're going to have to take this equation right here and isolate n out of it. Okay, so we're going to have a square root of 0.26 times, and 1 minus 0.26, I can do that, that's 0.74. And then we're going to multiply both sides by 1.960, or I don't need that 0 there. And then we're going to divide both sides by 0.05. And then on the right side, there's a square root of n. Okay, so square both sides. N is equal to 1.96 squared times 0.26 times 0.74, and then all over 0.05 squared. Okay, so let's get that into a calculator and see what we get. So 1.96 squared times 0.26. I know you can't see my calculator. I'm not changing my share screen here. I'm just going to try to do this as quick as I can. Divide by 0.405. Okay, so I plugged that all in quickly, and I got 295.65. 295.65. Okay. Now, obviously, we can't make our sample a fractional number of planes. So if we want to ensure at least 5% accuracy, we have to do more than this. So at least like 296 planes. So we have to test at least 296 planes. And then we'll get our accuracy within our estimate. So here our estimate was 26%, but that could have been like 7% away from the real answer. If we tested 296 planes again, then like our estimate would probably be something slightly different, but we would know that that estimate was within 5% of the real answer. Well, we wouldn't know. It's a 95% confidence interval. So there's still like a 2.5% chance that it's more than 5% too low and a 2.5% chance that it's more than 5% too high. But there's a 95% chance that we're within this desired level of precision from the real answer. Okay, so we'll do more confidence interval examples on Monday, but that's enough for today.